Okay, for all those who joined just now, so hello everyone, good evening, thanks for joining. So we'll wait for another couple of minutes and let others join, and after that we'll start with the session. Okay, thank you for joining. Okay, so it's 5 minutes past 6, so we'll start with the session now. Okay, so good evening everyone, thank you for joining. So this is week 10 of the CS100 course on operating system fundamentals. This is an NPTEL live session. So this week we will be solving a few numericals related to memory management and virtual memory towards the end of the session. So we previously in the week 9 session also we solved a few numericals related to memory management. So we'll continue to do the same. There will be a few theory questions also. Okay. So yeah, I am Somnath Hazra, a second year PhD student at IIT Kharagpur. So, yeah. Thank you for joining everyone. So let's start with the session. So this is the first question. So the percentage of time a page is found in TLB is called miss percentage, hit ratio, miss ratio, or none of the above. So what is it called? Would anybody like to contribute? So you can use the chat box as usual for all your answers or any queries related to anything, like it can be related to network issues also. We faced some network issues along the course, so anyway you can use the chat box. I forgot to tell you. So yeah, anybody would like to contribute? the percentage of time a page is found in the I hope you know what is translation look-aside buffer. So yeah, page is found in TLB. It is called miss ratio, miss percentage, hit ratio, or none of the above. Anyone would like to contribute? Okay, there's one answer. So anyway, let's go ahead. So this is called hit ratio. Okay, so what a translation look aside buffer does is that it stores a part of the page table. Since the page table needs to be stored in the secondary memory due to its size, so that requires two memory accesses, secondary memory accesses, for getting a page from the secondary memory, right? First memory access is from the page table, and then the actual page, the actual frame that is picked up from the main memory. So that requires two memory accesses. So in order to speeden up the process, the frequently accessed frames that are present in the main memory, those will be mapped, those entries from the page table will be mapped in a small part of the cache, which is called the translation look aside buffer. So that affords the double access of the secondary memory, of the main memory, primary memory, not the secondary memory, of the main memory, and that speeds up the process of bringing in a frame from the main memory to, yeah, so accessing a frame from the main memory. So that speeds up the whole process. We will look at a few more numericals also, how that reduces the effective access time. So let's go into the second question for now. So the TLB, as I said, is stored in, so the main memory, secondary memory, cache, or register. Anybody would like to contribute? So where is the translation look aside buffer actually stored in? Anyone would like to contribute? I'm waiting for answers. So where is the translation look aside buffer stored in? So in the previous session, we actually took up a few questions related to memory management, where we studied about paging and segmentation related things, right? So yeah, those are all ways to manage the main memory. So how paging differs from segmentation is that the complete main memory is divided into constant sized intervals, which are known as frames. So it's like the complete main memory is divided into chunks, equal sized chunks of memory. So that creates frames in the main memory. So those are mapped using page tables, which are different, which is created, which is an entry for all the processes that are currently there in the main memory, that is in the ready state. If I refer to the state transition diagram that we had studied long back. Okay, so there may be multiple processes that may be present in the ready state. For each process there will be a page table that will be created, and that will also be stored in the main memory itself. So this was done to overcome the external fragmentation, which was a problem in the segmentation process, where the whole main memory was not divided into constant size chunks. Instead, it was divided into spaces depending on the process that is currently being run in the secondary, in the main memory, those are currently brought in the main memory for running, right? So those are in the ready state. So according to that, the whole main memory is divided into some chunks of memory, like depending upon the methods that are present in the ready processes. So according to that, the whole main memory is divided into some chunks. So those are, since those are not constant size chunks, what that created was the problem of external fragmentation. So in order to overcome that, so the paging concept was brought into play, so which had constant space, which divided the complete main memory into constant constant size chunks. So we still have the internal fragmentation as a problem in paging, but the external fragmentation problem is removed, since the spaces that each process required, like the smallest spaces that each process required, those are constant. Okay, so that is about segmentation and paging that we had studied in the previous class. Anyway, let's get back to this question. So the translation look aside buffer is stored in main memory, secondary memory, cache or register. Anyone would like to contribute? I did not get any answers till now. Okay, I got one answer. I got two answers. What is the problem with the paging concept is that if the since the page table is stored in the main memory, so that requires two memory access in order to access a frame that is present in the main memory, right? So that creates a problem, because we have to access the main memory twice, although the main memory is faster than other forms of memory like the secondary memory, but it still accessing it requires more time. So, and accessing it for the page table, for a single page table entry makes a little sense, since we are not even bringing in the actual data that we require. So just to get the mapping, we are accessing the main memory. So as an alternative, what was created was the translation look aside buffer, so which is actually stored in cache. Okay, so which is faster compared to the main memory. So what that does is that reduces the effective so what that does is the frames that are frequently being accessed by a process, by a running process, those are loaded into the translation look aside buffer, which is actually a part of the cache. So that that is done with the intention to reduce the overall access time that is required to bring in a frame, okay, to read a frame from the main memory. Okay, so yeah, the answer for this question is cache. Okay, so now we'll look at a diagram at how this happens. So what the CPU generates, as we had studied in many of the previous sessions also, it is a logical address. So just give me a second. So it is the logical address that is generated by the CPU, which consists of the page number and the page offset that is signified by P and D respectively. So as I said, the translation look aside buffer is actually a part of the complete page table. You will know about page table from the previous classes. So yeah, so it is actually a part of the page table where which is stored in associative memory. What is the advantage of associative memory is you do not need to access the frames one by one. You can it can be accessed parallelly. So as you can see from the diagram, there are multiple arrows that are present. So actually multiple frames can be multiple entries can be looked at a single time parallelly. Okay, so the page number that we need for since this is actually not stored sequentially as in the page table, there can be random pages and random frame numbers corresponding to it. So we need to store both the page number and the frame number here. Okay, So it is not sequential as it is present in the original page table, as you may have guessed, since random entries may be put in there. So yeah, the page number entries are first matched using associative mapping. The corresponding frame, if it is a hit, the corresponding frame numbers are taken, and then we get the physical address using the page offset, that is D. Okay, so that gives us the physical address, and now we can access the main memory. If not, if it is a TLB miss, then we come to this section and we have to access the page table as usual. So that slows down the process a bit, you may think so, but the better the frames that are picked up from the page table, the entries that are picked up from the page table into this TLB, the chances of being a TLB hit increases, and that effectively reduces the access time of the reading an overall frame from the main memory. Okay, so we'll study numericals related to that next. Okay, so so this is a numerical related to effective access time. So consider a paging hardware with a translation look-aside buffer, and assume that the entire page table and all the pages are present in the physical memory, which takes 10 milliseconds to search the translation look-aside buffer, and 80 milliseconds to access the physical memory. Okay, now take the translation look-aside buffer hit ratio as 0.6. Then what will be the effective access time in milliseconds? So all the details in this numerical are given, that is you have to so if you consider the bold details that are present, so 10 milliseconds is the time that is taken for access of the translation look-aside buffer. For access of physical memory, 80 milliseconds is required. Now the hit ratio of the translation look-aside buffer is 0.6, and you have to use this formula to calculate the effective memory access time in milliseconds. Okay, so everything is given in milliseconds, you do not need to worry about that. So what is this formula? Let me just give a brief explanation about what this formula actually says. So H is the hit ratio, AT refers to the access time of TLB. Yes, I got one answer. So anyone else would like to contribute? So you may use the chat box as usual. Okay. So AT-mem means effective access time of the main memory. Okay, and this is when when there is a hit of the translation look-aside buffer. So if it is a hit, then we require the access time of the translation look-aside buffer, and then we can take out the frame from the main memory. And if it is a miss, then we obviously require the access of the translation look-aside buffer. Only then we can know that it is a miss. But after that, since it is a miss, we have to actually access the page table that is present in the main memory, as we saw in the previous diagram, and that creates two accesses of the main memory. Okay, so as I was saying that if the H part is bigger, that is if this fraction is bigger, then this effective access time actually decreases by a great margin. Okay, so anyway, I diverge again. So yeah, coming back to this question, so anyone else would like to contribute? I got one answer. Otherwise we'll go to the answer now. Okay, let's go to the answer. So yeah, what details are given is the hit ratio, which is 0.6, access time of TLB is 10 milliseconds, and access time of main memory is 80 milliseconds. So the effective access time is, you just need to simply put it in this formula and you will get it is 122 milliseconds. That is correct, 122 milliseconds. Okay, thank you. So anyway, let's move on to the next question. So every address that is generated by the CPU is divided into frame number and page number, page offset and frame number, page number and page offset, frame offset and page offset. So anyone would like to contribute? So what is the address that is generated by the CPU actually called? So it is the logical address, right? So yeah. Okay, I got two answers. So yeah, as I was saying, the CPU, the addresses that are generated by the CPU, those are the logical addresses, right? So what are the two parts of the logical address? That is the answer to this question. What are the two parts of the logical address? So if I go back to the diagram here, so this is the logical address right here. So these are the two parts, P and D. So what are these two parts called? So I have two answers. Anyone else would like to contribute? Okay, let's go to the answer then. So yeah, it is C, that is page number and page offset. Okay, so as I was saying in the previous explanation also, this is the page number as it is written here. So yeah, page number, and D is the page offset. Those are the two parts of logical address that is generated by CPU. Anyway, let's get to the next question. So this is another numerical. So consider a 3-level paging scheme. So as you may know that sometimes a single page is not enough, and there may be levels of paging scheme. So we do not need to go into the details of that right now. So for this numerical, whatever details you require, I'll provide it anyway. So consider a 3-level paging scheme with a translation look aside buffer. So and assume that no page fault occurs. So there is a significance of this statement. So in the previous numerical also we had I had said that there is no page fault that you need to assume. So there actually comes the concept of virtual memory. So we'll study a bit about that in the later part of the session. Anyway. So it takes 20 milliseconds to search the translation look aside buffer and 100 milliseconds to access the physical memory. So if TLB hit ratio is 80%, the effective memory access time in milliseconds is what you need to calculate. Okay. So what you need to consider is 3-level paging scheme. 20 milliseconds is the time to search the TLB, 100 milliseconds is the time that is required to access the physical memory, and hit ratio is 80%. Okay. So yeah, you can use this formula for this problem. So the effective access time for multi-level paging scheme, where the number of levels are signified as L, which is 3 here in this case. So how does that change from the original formula? This part stays constant. That is, if it is a TLB hit, it is actually the same. Okay. And if it is a TLB miss, then there are multiple levels of pages. Okay. So in that case, what happens is that for each page there is a main memory access, plus there is one extra main memory access that always stays for accessing the actual frame, actual data from the main memory. Okay. So there is L plus 1 accesses of the main memory if it is a TLB miss. Okay. And obviously there is one access to the TLB always. It is independent of whether it is a TLB hit or a miss. So Since you have accessed the TLB, you know that it is a hit or a miss. And the other details that are provided is that the access time of TLB is 20 milliseconds, the access time of main memory is 100 milliseconds, number of paging levels are 3, and TLB hit ratio is 0.8. So anyone would like to contribute? Yeah, so anyone would like to contribute? I got one answer. Okay. Okay, I got another answer. So let's get to the answer now. Okay, so yeah, this is the overall what you have to do. So if it is a hit, this part is the hit, so it is 0.8, the TLB hit ratio. It is 20 plus 100, that is 120. If it is a miss, 0.2 part. Okay, it is 20 plus 3 plus 1 is 4 into 100, that is 420 plus 20. Sorry, 400 plus 20, that is 420 into 0.2 plus 120 into 0.8. Okay, so I also got this same answer. So it is equal to 180 milliseconds. Okay, so this part is coming up to be 84 and this part is 96 according to my solution. Yeah, this part is. So if you have any doubt, you can use the chat box, but I think it is correct. Anyway, let's go to the next problem. So consider a single level paging scheme. It is not a multi-level paging with a TLB. So assume no page fault occurs. So it takes 20 milliseconds to search the TLB and 100 milliseconds to access the physical memory. If effective access time is 130 milliseconds, the TLB hit ratio is, now in this question what you need to find is the TLB hit ratio. What is given is, it is a single level paging scheme. 20 milliseconds is the access time of TLB, 100 milliseconds is the access time of physical memory, and effective memory access time is 130 milliseconds. So what is the formula that you need to use is, if I get back just for once, so this is the formula that you need to use, right? So yeah, getting back to the question, this is the question. So anyone would like to contribute? So if I go to the summary, what is given is number of levels of page table is 1, TLB access time is 20. Okay, I just made a mistake. Okay, I have written everything in nanoseconds here. There is just one correction. Everything will be in milliseconds instead of nanoseconds. Okay. Anyway, so main memory access time is 100 milliseconds and effective memory access time is 130 milliseconds. So what is the TLB hit ratio? If we consider H as the TLB hit ratio in the formula that was previously given, what comes up? So the TLB miss ratio then comes out to be 1 minus H, right? So yeah, solve it accordingly. It's just a single level of paging. Okay, so if I use the formula, what comes up is uh, 120 into H plus 1 minus H into 220, that is 200 for the memory access time, main memory access time, and 20 for TLB, that is equal to 130, that is the effective access time. So you just need to find H. Anyone would like to contribute? I got one answer. Okay. Okay, I got two answers. Anyway, let's get to the answer now. So yeah, the effective access time, as I was saying, that H into 120 plus 1 minus H into this comes out to be 220, that is equal to 130 milliseconds. so h that comes out to be 0.9. Okay. If anyone has any doubt, you may use the chat box. Okay. Let's get to the next question now. So which among the following are correct? Linked list resolve collisions in hashed page tables. Inverted page table consists of an entry per page. The hash value directs an entry in the hash table. Chained pointer is used to resolve sharing in inverted page table. So don't worry, I'll tell about chained pointer if you do not know about it. So anyone would like to contribute? Which among the following is or are correct? Okay, I got one answer. Look at the theory related to hashed page tables and inverted page tables. But first, anyone else would like to contribute? So what chained pointer is that how do you resolve sharing in inverted page table? So what inverted page table stores is that instead of storing a page table per process that is actually present, it actually stores a single page table for all the entries related to all the ready processes that are present in the main memory, and all the entries that are present, all the page entries that are present in actually in the main memory, it stores one entry per page. Okay, so that is what the inverted page table is. Instead of storing entries for the virtual memory, it stores entries for the main memory. Okay, the inverted page table. So that actually reduces the size of the page table, since whatever pages are not present, those are actually never indexed into the page table. Okay, but there needs to be an extra entry that is related to the process. So each process also the process number, the PID, process ID, that also needs to be stored in the page table also. Okay, so what chain pointer does is that there may be sharing of a section of the main memory among multiple processes. So what chain pointer does is that it actually creates a pointer to each of the processes. There may be multiple entries, so it creates a pointer to those entries for the multiple processes that are sharing that part of the main memory. Okay, so it actually looks like the chaining process of the hash table when there is a collision. So anyway, I diverge. Let's get back to this question. So anyone else would like to contribute to the answer? I got one answer, two answers. Okay, so this is the answer to this question. So linked lists are actually what happens if there is a collision in hashed page tables is that there is the process of chaining, as I was saying. So linked lists are used in those cases. So we'll look at how linked lists are used in those cases. So which actually creates enables us to map into a single location of the page table, map multiple entries into a single location of the page table, and the hash the inverted page table actually consists of one entry per frame, which is a part of the main memory. Frames are a part of the main memory, pages are a part of the virtual memory. Okay, so that statement is incorrect, and the hash value, yes, directs an entry in the hash table. Okay, that is correct. And chain pointer is, yes, it actually is used to resolve the sharing of inverted page table. Okay, so yeah, let's get to the idea of hashed page table and how linked lists are actually used. So what happens is that if a hash function maps to a single location in the hashed page table, so for for multiple pages, so what happens is that for each of the pages that are mapped into that single location, there is a linked list that is created. Okay, so as you can see, which consists of the page number, okay, the corresponding frame number, and the pointer to the next entry. Okay, so this is how the hashed page table looks, and this is actually a linked list. If you have studied hashing in data structures, so this is how you actually resolve collisions in hashing. So this is actually chaining, that is a collision resolution technique that is actually used in hashing. So this is the actual chain that is created to resolve the collisions. What collisions are? That multiple, if a hash function maps multiple pages into a single entry of the hash table, the hashed page table. So as you can see, if I require the physical address for this logical address, so P3, the entry corresponding to P3 is actually picked up the frame number, and then we can obtain the physical address. So this is hashed mapping. This is the inverted page table, okay, where the entries are corresponding to the physical memory frames instead of the virtual memory. So the page table entries correspond to the physical memory in this case. So that is why there are two entries that need to be stored for each of the entries in the page table. That is the process ID, PID as said here, and the page number. So we cannot anymore index using the page number here. We have to linearly search or find some other usable search technique, effective search technique to search this kind of page table. So as you may remember, in previous cases what used to happen is that this page table was indexed by using the page number. So when there was the concept of page tables from the virtual memory, but since this is created from the physical memory, so in that kind of indexing is no more allowable here. The indexing actually happens on the basis of the physical memory addresses. So that is why that is how this value I is picked up, and that actually creates the actual physical address with the offset staying the same as usual. Okay, so this is the concept of inverted page tables. Okay. So as you can see, the linear search technique is applied here. So it does not depend on how many processes are there that are present in the ready state. So there is just one single page table that is created for all the addresses that are present in the physical memory. Okay. Sorry, for all the frames that are present in the physical memory. Okay. Anyway, let's get to the next question. So when does a page fault occur? When a page gives inconsistent data, when a reference page is absent from the main memory, when a page is not present in the TLB, or none of the above? Okay, I got one answer. Okay, let's get to the answer then. So yes, this is the answer to this question. Yeah, when a reference page is actually absent from the main memory, that actually creates a page fault. So when there is a miss from the TLB, when a page is not present in the when a page entry is not present in the TLB, that actually creates uh, that that is referred to as the hit and miss of the TLB. Now this is the page fault, which in which case the page is altogether not present in the main memory. If you remember, in the previous questions we had the numericals that we had studied, there was an assumption that was taken, that is no page fault occurs. Okay, now the concept of page fault has come into play, which says that altogether this page is currently the page that is that we want to access, that is not even present in the main memory, it is present in the secondary memory. So these concepts come into play in the case of virtual memory, and when a process of huge size of size that is greater than main memory, that is allowable that is present in the total system, so that process is running. For example, a process that is of size 6 GB is running in a system that has a main memory capacity of 4 GB, which actually happens in many modern day systems. So in that cases, the concept of virtual memory actually comes into play, which gives the virtual idea that the complete secondary memory is actually the main memory. So it is not true, but in order to clarify the picture a bit, so that can be thought of. Okay, that is the concept what can be thought of. So yeah, when a page is totally absent from the main memory, that's when the page fault occurs. Okay. Anyway, let's get to the next question. So where does the swap space exist? So this is a question from the previous session actually. So we studied about swap space a bit. So where does it exist? Secondary memory, primary memory, cache and registers. So where does this swap space exist? Anyone would like to contribute? Okay, I got two answers. Okay, yes, it is present in the secondary memory, it is a part of the secondary memory. So as I had said in the previous session, if you had installed a Linux distribution on your own, like Ubuntu or something like that, so in that case there actually comes up a part in the GUI installation process where you have to determine the amount of swap memory, right? You have to create the swap space, and it is recommended that you keep it equal to the size of the main memory that you have. Okay, so that is where the swap space comes into play. And we had studied that the processes, the frames that are unused in the main and are kept in the main memory. So in order to get more of the active frames that will be used currently into the main memory, so we swap out some of the main memory unused main memory frames into the secondary memory. Okay. So that is where this swap space comes into play. Let's get to the next question. So virtual memory is implemented by which of the following: bus, demand paging, virtualization, or none of the above? Anyone would like to contribute? Okay, I got one answer. Okay, I got two answers. Anyone else would like to contribute? So yes, the answer is actually demand paging. So what happens in demand paging is that, uh, as I said, virtual memory actually creates the concept that the complete secondary memory is a part of the main memory, and so that even if you do not have enough space in the main memory to allocate to a single process, you can still run the process depending on the pages that are immediately required. It may be a bit slow, it may be a slower process, but it actually works. So what happens is that, if from the CPU there is a memory reference that is created, so which is actually searched in the main memory. So since it is actually pointing to a page that is invalid or that is not present in the page table, so that creates a trap, and the signal is sent to the operating system, and operating system actually picks up that page from the secondary memory. This is the complete secondary memory. It brings that page into the main memory, then replacing a single frame, replacing a free frame from the actual physical main memory, and then that entry needs to be updated into the page table. So that is actually done, and then we restart the instruction. So load M is the instruction. Load, if you have done 8085 computing, you may know what is a load and store, or you will come to know later. So yeah, these are actually lower level instructions when we want to access a memory location and bring it into the registers. Okay. So this is the concept of demand paging. When there is a demand for a page, when we require access of a page, at that time we bring it on from the backing store, which is a part of the secondary memory. Okay. So when we require access to a page, at that time only. Okay. So there is this concept of starting with no pages in the page table for a process. Okay. And as we require, so that is known as strict demand paging. So we start with nothing with the page in the page table when the process is created in the running state. Okay. For the first time, and as we require pages from the main memory, as we require pages, we pick it up from the secondary memory and update the page table accordingly and replace those pages in the physical main memory. Okay. So yeah, this is strict demand paging. As you may have guessed that it slows down the process, but it actually helps to run processes that are that require much larger space than what is allowable by the physical memory, the complete physical memory itself. Okay. So, yeah. Let's get to the next question. So with reference to virtual memory, which among the following are true? Virtual memory is an illusion of extremely large main memory. Virtual memory is an extremely large secondary memory. It requires hardware support, and pure demand paging starts a process with no pages in the main memory. Sorry, I said strict demand paging. It is pure demand paging. Okay. So anyone would like to contribute? Which among the following is or are true? There may be multiple correct statements also. Okay, I got two answers. So I was explaining strict demand paging. It is not strict demand paging, it is pure demand paging. So as I was saying, that it starts with no pages in the main memory, no pages related to the process, the page table is completely empty, and as there is a demand for the pages, those are actually replaced in the main memory and the page table is updated sequentially. Okay. And yes, it requires hardware support obviously, because without the concept of OS actually creating that, it requires the uh, because you need to trap those instructions. The operating system need to trap those instructions. If there is a page fault, that the OS needs to understand that it may be present in the secondary memory, and the page table needs to be updated. So the main memory can be updated, since the page table is actually a part of the main memory. So the parts of that page table needs to be updated in the dynamically, right? So all those require hardware support. Okay, virtualization concept. And yes, it is obviously true that the virtual memory is an extremely large main memory. So yes, except for B, uh, rest of the statements are actually true. Okay. Okay. So we come to the end of the session. Thank you everybody, as usual. Uh, uh, we will meet in the next Tuesday's class for the week 11th session, and thank you for joining. So I know it is a time for holiday, but still you joined, so thank you for that. uh, yeah, thank you. Yeah, bye bye. So you may drop off for now.